Back? Alright, we're back. Hello everybody, it is 3:30, which of course means it is time for one of our afternoon STEM shows here at the Headwaters Science Center. My name is Ryan, I'm one of the educators here. If you watch these shows, you've seen plenty of me, you know who I am. And we're up in my office today, which of course means we are doing kind of a react video. And today we are particularly going to be following up the story that Lee read yesterday. One of the stories. He actually read a couple of books yesterday, but this one in particular is the one that I kind of took a specific interest in. It was called How Big Are Dinosaurs? And I actually really liked this book because, you know, we had a live audience yesterday. That's always fun when you're doing these shows for a live audience. And of course, you know, he said, how big are dinosaurs? And some kid in the audience was like, they're really, really big. They're huge. And I said, one of the things I really like about this book is that it shows that not all of them were huge. You know, it talks about some of the smaller ones in here that are kind of interesting. So it talks about, you know, this guy being about the size of a chicken, and this one being the size of like a young rhinoceros or an emperor penguin or a golden retriever, a bunch of these different dinosaurs being a bunch of different sizes. And then of course it does eventually scale up to some of the real big ones. You know, it talks about Argentinosaurus, which is, as far as we know, the biggest land animal to ever exist, the biggest terrestrial animal, because it's weighed more than 17 elephants. And so I think what I wanted to talk about today is like how does that happen? How does an animal get that big? Why we don't see animals that are that big anymore, at least not terrestrial ones? And like, what are the advantages and disadvantages of that? How does being like that big really affect you? And so I think just to start, we're going to hop into a PBS Eons video here, because they, sorry about that, because they, of course, as they tend to do when I find some fun topic to talk about, one of the first things I always do is see if I can't find a YouTube video that talks a little bit about it, and oftentimes PBS Eons has got me covered, so we're going to see what they have to say about it. I actually haven't watched this video yet. Sometimes I pre-watch the videos just to make sure their information in them's good, but I trust PBS Eons, so we're going to swap over to that, and we'll hop right into it.
Part of why we're so fascinated with extinct dinosaurs, I think, is that some of them were just so big. It is hard to imagine animals walking around on the surface of the planet that size. Speaking as a mammal that's about 2 meters tall, I gotta say, it's hard to grasp what it would be like to be in the presence of a creature as tall as a 5-story building. And yet, they existed. From the Jurassic to the Cretaceous periods, when our ancestors were the size of voles and shrews, dinosaurs like Supersaurus, Sauroposeidon, and Argentinosaurus were shaking the earth. So how did they get to be so big, and why did we mammals never even come close to dinosaurs in size?
And this is a relatively short video, so I'm probably not going to be interrupting it too much as we go forward. But one thing I do want to talk a little bit about here is how he's talking about kind of the time period of this. These are the Jurassic and Cretaceous, so these are kind of the ones it sounds like he's going to be talking about are like the biggest ones, and they're kind of from the kind of later ages of the dinosaurs. But there are older big sauropods that are still like way bigger than any modern day animal is, any modern day terrestrial animal again. So this isn't a thing that's like unique to this one, you know, 100 million year stretch kind of in the latter half of the dinosaur years. There are other big dinosaurs that predate this and are bigger than anything modern.
Well, to our credit, the most massive animal ever is, of course, a mammal, the blue whale. It can get up to 30 meters long and weigh as much as 145 metric tons, more than twice as heavy as the most massive known dinosaur. But to be fair, the rules of biomechanics are different in the water. Buoyancy and blubber can do amazing things, allowing sea creatures to grow to sizes that would be impossible on land. But when it comes to the largest terrestrial animals, mammals were never any competition for the non-avian dinosaurs. There's always been some debate about what the biggest dinosaur was, but but the current record holder for the largest specimen belongs to the newly named titanosaur Patagotitan. Experts estimate that this Cretaceous herbivore stretched over 36.5 meters and weighed upward of 64 metric tons. By contrast, the biggest mammal that ever walked on land was the hornless rhinoceros, known as Paraceratherium. It weighed a mere 15 tons and stood about 5 meters high at the shoulder, roaming Eurasia from Romania to China at the end of the Oligocene epoch, long after the non-avian dinosaurs disappeared. So how can two such successful and prolific types of animals end up having such different size constraints? Part of it might have to do with how they reproduced. Paraceratherium was a placental mammal like us, meaning that it gestated its young inside its body. And if this ancient rhino was anything like large mammals we have alive today, that would have taken a very long time. Big mammals like giraffes, rhinos, and elephants usually only have one offspring at a time, and gestation can last longer than some other kinds of animals live. Elephants, for example, carry their babies for more than 2 years. Now consider the dinosaurs. They didn't really have to carry their babies at all because all the dinosaurs laid eggs. Even the biggest of the giant dinos hatched from an egg no bigger than a soccer ball. What does this have to do with size? Well, bigger mammal species give birth to bigger young, which requires a huge amount of time and energy to gestate. Dinosaurs totally bypassed that problem. Instead of having bigger babies, the largest dinosaurs laid comparatively small eggs, which held equally small hatchlings. Reproducing this way, with babies hatching and growing outside of the mother's body, removed the size limit that gestation places on mammals. Dinosaurs also had another evolutionary advantage. Their skeletons had a special feature that mammals lacked: a sophisticated system of air sacs. These sacs were basically pockets of soft tissue that were connected to the lungs. Think of them as biological balloons. Some of these sacs sat in the body cavity next to bones, usually in the neck, back, and hips, but others ran inside the bones themselves. These air sacs helped shape the dinosaur's skeleton and allowed the bones of the biggest dinosaurs to remain light without sacrificing strength. How do we know that extinct dinosaurs had these sacs? Partly because the non-extinct dinosaurs have them too.
Yeah, and that's exactly what I was going to say. Is it sounds very similar to how like birds operate, where they have a, the actual like bones in their skeleton are relatively light and frail, but they have this like system of air sacs that help give structure to the skeleton, but also are important when they're respirating as well, which it looks like he's about to get into here, is kind of the uniqueness of bird respiration as it is related to this. But yeah, he's touching on kind of a really interesting point here where he's talking about just like the physics of like being that big. And that's something I was planning on talking about afterwards if he didn't. It is really tricky to like be of that kind of scale. And as they mentioned, we see a lot of these really, really big creatures end up living in the ocean just because like buoyancy is pretty cool as far as like needing to maintain that much weight. But it comes into play with things like height too. Like you can think about like the physics of like needing to like pump blood like up to a giraffe head. Like a giraffe has to have a relatively large heart for its body, just for the sake of being able to pump blood that high. And then, a giraffe is a fraction of the size of some of these big sauropod dinosaurs that he's talking about. So it's a interesting challenge that, you got to kind of work your way around when you're this big, and particularly this big on land.
Birds have a similar system of sacs that help draw air into their tiny lungs while also making their skeletons remarkably light. And if you compare the respiratory system of birds to those of the giant dinos, you'll see the resemblance is pretty striking. In sauropods, for example, the vertebrae of the back and neck have the same pockets and divots we find in birds today, where these air sacs were attached. And when paleontologists scan fossils of some dinosaur bones, like vertebra, they often find hollow spaces inside the bones where the air sacs used to sit. Now keep in mind that bones with spaces created by air sacs are different from the hollow bones that you see in the legs of birds and other theropod dinosaurs. And not all of the extinct dinosaurs had these handy airbags. Only the type of dinos known as Saurischians had them. In the traditional dinosaur family tree, this group encompasses the theropods, that is the two-legged dinosaurs that include today's birds, as well as the sauropods, the quadrupeds that include the giant titanosaurs. All of the rest of the dinosaurs, like the horned, armored, and duck-billed dinosaurs, are known as Ornithischians, and they didn't have these features, so they weren't as light on their feet.
And of note, we don't have Ornithischian dinosaurs anymore. That's a lineage that has died off. The Saurischians, though, do still exist in the form of modern birds, which he's touched on a little bit here. But we don't have a good modern comparison for Ornithischian dinosaurs.
Of course, we mammals don't have anything like them either. We retained a skeletal system of dense, heavy bones that puts a limit on how big we can get before our bones crack under our own weight.
And what he's talking about there, again, skeleton-wise, is it's kind of an interesting thing, is that you'll see in a lot of big mammals, like you can see this in like bison, for example, is something that we have relatively close to Bemidji here that has some special kind of skeletal adaptations to accommodate even that amount of weight, which is, again, like a fraction of what we're talking about with some of these bigger dinosaurs, where you'll see that like the tibia and fibula, the like shin bone and other one in the lower leg, are fused in a lot of these big hoofed animals, because the extra strength that grants is more valuable than the reason we have two bones, and the reason a lot of animals have two bones in their lower leg is it helps with rotating. You have the same thing in our arm. Like the fact that we can do this is a product of having two bones in our forearm, and like I said, it's the same with our ankle and our lower leg. But when you get to a certain size, all of a sudden, like that flexibility becomes a liability because it's weaker. And so you see in a lot of these bigger mammals in particular, you'll see those bones start to fuse together and you lose, like I said, flexibility in them, but extra strength is more valuable for a big thing like that.
The thing is, these adaptations are just what allowed dinosaurs to get so big. They don't tell us why these giants got so enormous in the first place. And that's a totally different evolutionary question with lots of possible answers. Maybe living large was a way to stay safe from predators. Or maybe their size allowed dinosaurs to cover more ground or reach higher leafy branches in search of food. Or maybe there's something paleontologists haven't thought of yet. And then there's another question to consider. Was the ability to grow so large really an advantage? After all, the sauropods are gone. So are most of their relatives. Of the entire dinosaur family, only birds, a single group of saurischian theropods, survives, and they range in size from the hummingbird to the ostrich. So today, even if it's hard for us to picture a dinosaur as huge as Patagotitan, we can at least understand how animals like it were physically possible. Perhaps we're lucky that we never reached such great heights. Evolutionarily speaking, it seems that bigger is not always better.
And that's a weird sentiment to end on, in my opinion. Let's swap over to my full screen here. Like the bigger not always being better sentiment there that he was kind of alluding to at the end. He's saying, you know, this was probably not that advantageous because these animals eventually went extinct, is really interesting because as it stands, like those animals lived a lot longer than like any big-ish mammal ever has. Like we had big sauropod dinosaurs for, I said, 100+ million years, which mammals ain't done that yet. Like, and so it's interesting because a topic we've talked about on a few occasions here is talking about how animals end up adapting to the environment that they exist in, and that's why things like climate change are such a problem, because when environments around animals change, the adaptations they have to the previous environment no longer become applicable, and in a lot of times can even be directly harmful. And so I don't think that an animal going extinct is necessarily an indictment on that animal's fitness in the era that it existed in. Said when major change happens, other major changes happen, and you end up with species that go extinct. But I think it is worth talking about like what the advantages are of being big, because if they're going to get that big, like there must have been some sort of selection pressure that was like forcing them into that size. And I think it's important to kind of talk about that. He touched on it a little bit. There's probably a few different models for it. But one of the things he alluded to is that being that big is beneficial in that it allows you to avoid predators to a certain degree. Because when you're that big, you know, I think about it like an adult elephant today. Like if you're an adult elephant, you like don't have predators besides humans. It's like not a thing you have to worry about, really. You don't have to worry about, you know, lions coming and eating you or hyenas coming and eating you, because what are they going to do to you? Like, you're too big. So that, like, generally is thought of as kind of the biggest advantage of being really big, is that, like, that gigantism provides you, like, a certain level of protection just from, like, predators in general. The other thing, particularly that is important with mammals to think about is that as mammals get bigger, we tend to get more efficient, basically. Like, I don't need to eat nearly as much food for my body weight as a mouse does in a given day. And an elephant needs to eat even less than I do. Like, as you scale mammals up, we get more efficient relative to our body weight. So like a shrew or a mouse or something like that has to eat like several times its own body weight worth of food in a given day just to sustain itself. Whereas an elephant, is it like 5-10% of its body weight it's got to eat in a given day, something like that. Just substantially less, obviously. They do need to eat, like, in raw terms, they have to eat more food, but relative to their body weight, like I said, they get a lot more efficient. There's even some models that talk about it kind of in the context of like biomass in that regard too, where you'll say, you know, you have an elephant. If you take an elephant and then take like a comparable number of gazelles by weight, or zebras or some smaller animal, like you can sustain, how heavy's an elephant? You can sustain that weight in one big animal a lot more than you can sustain it in a bunch of little animals. So there's a certain like biomass element to it too that, you know, you hear people talk about sometimes. And you can also eat just like worse food. Like a lot of these big animals, these giraffes, these elephants, these rhinos, hippos, they eat kind of garbage. Again, because their digestive tracts and bodies just operate much more efficiently than what, you know, like a mouse does. Mice. You know, there's a reason they like our big mouse issue in the Headwaters Science Center is they get into our bird seed. And there's a reason they're going for that bird seed is because it's really nutritious for them. It's a really high fat content, really high caloric content item that they really, really like. There's a reason they go for things like peanut butter and things like that. Because they need that type of food to sustain themselves when they're that little and that inefficient. And so, like I said, if you're an elephant, you just sit there and you browse on garbage, grass, and leaves all day, and you can sustain yourself on that, and the size is a big part of what facilitates that. As far as disadvantages, you know, why isn't everything huge? The obvious thing is that, like, even though they are more efficient with, like, relative to body weight with how many calories they need to take in a given day, they still need to eat more food, so they are very much more limited in population. You know, there's way more mice in the world than there are elephants, and there always has been and always will be. The other thing it does, and we talked about bigness as a protection against predators, but it also is something that very much restricts like the way you can protect yourself. Like an elephant can't climb a tree to get away from a predator. An elephant can't fly. An elephant can't dig a burrow. An elephant can't like run away quickly. Like really the only option it has is being big, and that goes all the way down to like even before it's big, to be honest. A baby elephant can't climb a tree to get away from a predator either. And so there's a weak point when they are not big that causes success rate for as slow as they reproduce, the success rate of those babies reaching adulthood is not always great as far as like sustaining their numbers. It's better than what it is for, you know, a lot of these small critters, but it's not necessarily enough for how relatively slowly they reproduce to like really fill up a population space, really fill up an ecosystem with themselves. And we talked briefly already about just kind of the general physics of it being tricky. There's specific adaptations that your body has to have in order to sustain that much weight. The other thing that they didn't really talk about in that video that I did kind of want to touch on actually is like why in the dinosaur context, like, because we were talking a lot about big mammals because that's what we have right now that's big, you know, hippos, rhinos, elephants, giraffes, or, you know, the biggest terrestrial things we've got these days. They're all mammals. We don't have a reptile that really even is close to that scale weight-wise. But like I said, we used to. And we had reptiles that were much bigger even. And so how did that happen? And why doesn't that happen anymore? And this is going back to this climate thing. When you're a reptile and you're cold-blooded, or even when you're not like truly cold-blooded, that's a different conversation. The temperature that you're living in, the climate that you're living in, has a big impact on how quickly you're able to grow. And so we're living in a relatively cooler time now than what we were in the Jurassic and Cretaceous period. The other thing that's very different now compared to what the Jurassic and Cretaceous periods were like is that we have not nearly as much CO2 in our atmosphere as we did back then. And so what you saw back then was there was this really hyper CO2 inflated atmosphere that these dinosaurs were living in, and things that love CO2 are, plants. And so you had this environment where you had this really hot climate with all this CO2 in the atmosphere that really facilitated a lot of plant growth. And so you had more plants around for these big things to eat. And you'll notice that like all the stuff he was talking about in this, when he was talking about the biggest dinosaurs, were all herbivores. And so you have this warm climate and all this food around that facilitates these dinosaurs getting big-ish. But as is wont to happen in nature, you get kind of this arm race between herbivores and potential predator carnivore animals, where you get like a bigness that happens just from like, yeah, I can do this because there's enough food to sustain it. But then you get the additional selective pressure on top of that, and that being bigger helps keep you from getting eaten. And so you, like I said, kind of get this arms race where you get the herbivores getting bigger, and then you get the carnivores that are getting bigger to try and take down those herbivores that are big. And so you start seeing, the theropods, your T-Rexes and friends, getting bigger and bigger and bigger as a means of like having a chance of taking down these big herbivores that are existing because of all the plants. And then, like I said, you get this big climate change event at the end of the Cretaceous period where you get this big cooling off period, and you see a big change as far as the plant life that's existing. And all of a sudden, you can't sustain these big bodies anymore. The sauropods fall off, all these other big herbivores fall off, and then all of a sudden, if you're a T-Rex, like, what are you eating? Like, there's nothing big enough prey item wise to sustain you anymore, so you end up dying off too. It causes chain reaction where all of a sudden the selective pressures that made the things big are gone, so there's no reason to be big anymore because it just means you have to eat more food, and they go away. And that's, I said, ultimately what happens kind of at the end of the Cretaceous period. That's why we don't see things like, your titanosaurs around anymore, because there's not enough food for them, and because there's not enough food for not even just titanosaurs, but, your stegosaurs and your ceratopsids. The things that existed to prey upon those things can't sustain themselves anymore either, and that's why you don't see your big theropods anymore. And all that we have left of the dinosaurs now are the birds, who are small and warm-blooded and prey on much smaller things, mostly small mammals, that become much more abundant in that time period. But yeah, I think that's a good spot to call this a topic. We've been live for 20 minutes or so now. I said we got a big event happening tonight, so I'm kind of squirreled away in my office here, getting this out quick for you. But thank you guys for watching. Headwaters Science Center is open 7 days a week right now. We are open Monday through Saturday from 9:30 to 5. We are open Sundays from 1 to 5, so swing by after lunch on Sundays. Tomorrow, since we're talking about dinosaurs, we actually have an event happening, and there's a couple slots open for it yet, where we are going to be doing, actually I have right here, a dinosaur painting night. And so one of our other educators, Carl, is hosting this, and basically what it is you'll come here and you'll get a 3D printed, this month it's a Spinosaur, and under Carl's watchful eye, under Carl's guidance, you'll do some painting with it. And it's a fun topic to talk about. We talked about dinosaur size today, but we haven't really talked in a while, at least, about kind of how we know or think we know or kind of speculate on how dinosaurs looked color-wise. It's something that, is an interesting topic to talk about, and is going to be presumably something that Carl's talking about tomorrow. And so if that sounds interesting to you, you can call in at the Headwaters Science Center, 218-444 it's 444-4HSC, whatever the digits end up at, but 444-4HSC. And like I said, there's a few slots left in that, so if that sounds interesting to you, it's tomorrow from, I believe, 5 to 7. think it's $20 to get in. So yeah. Anyways, thank you guys for watching. What's tomorrow? Friday. I'll try and come up with some other dinosaur-y kind of topic for tomorrow at 3:32. But hopefully we'll see you tomorrow. And like I said, I got to go do some setup for this event. So thank you guys.